Okay, so now we have the Feynman rules and we can use them to calculate things. But in practice, we're pretty much out of time. So I'm not actually going to do anything more quantitatively. Instead, I'm going to just sort of vaguely argue for what can happen. And so this pretty much ends the precise part of the course. From now on, I'm going to be kind of hand wavy. Okay, so sit back and relax. From now on, everything's going to be qualitative. So let me remind you about something that happened when we did the one loop correction in 2 to 2 scattering in phi to the fourth theory. So if you recall, we calculated this correction, and so at tree level in phi to the fourth theory, we had a term that looked like this. And then the one loop correction involved some more diagrams that looked like this. There was one like this, one like this, and one that I always have trouble drawing. That's something like this. You get, that was a terrible failure. There we go, you got the idea. Okay, and we calculated these, right? This was order lambda. These were all lambda squared times some complicated loop integrals. And we found the invariant matrix element to be Im equals to minus I lambda squared over 32 pi squared times stuff. And the stuff, for example, was something like log of S over S naught plus blah, 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 where there was also the Mandelstam parameters T and U appearing there. And if you recall, S was sort of the energy of the particles coming in. Okay, it was like P1 plus P2 or something like that. So S is basically the energy involved in the collision. Okay, so now, oh, and finally, S naught was the renormalization point. Okay, so now let's take a second and stare at this and think about what does this mean about how the interaction changes with energy. At tree level, the scattering amplitude doesn't seem to depend on the energy at all. Now, what happens if we increase the energy in the collision? Well, notice that increasing the energy now at loop level changes the interaction strength, and it acts in the same direction as making lambda bigger. Okay? So in other words, what we say is that increasing energy makes the interaction stronger because it acts in the same direction as making lambda bigger would have. Okay? So the scattering amplitude becomes bigger and bigger as you increase the energy. So note also that this depends crucially on the sign here between these two terms. If that sign had been the opposite, we would have come to the opposite conclusion. Okay? In that case, increasing the energy would have decreased the interaction strength. But this is what we found. We did a careful calculation and calculated that sign. And so we find that in lambda phi to the fourth theory, increasing the energy means the interaction becomes stronger. And you can do a very similar calculation for QED, and you would also find the same thing, that increasing the energy makes the interaction stronger. So in other words, in both of these theories, the interaction is stronger in the UV, in other words, at short distances at high energies. Okay, so now this is the same thing in non-abelian gauge theory. And the goal here is to understand whether it gets stronger or weaker as we go to high energies. So we need to pick some process, just like here we pick 2 to 2 scattering, we need to pick some sort of interesting process in non-abelian gauge theory. So there are many things we could pick, but remember there's only one coupling in the theory, there's only one coupling G, and so they're all controlled by the same coupling, so we get the same information no matter what process we pick. So let's pick, for example, quark scattering with a gluon and calculate this, okay? So at tree level, this thing goes like G, and then at loop level, there's a bunch of diagrams. So for example, there's a diagram like this. This is a quark line, and then there's a diagram that looks like this. Okay, and then you should also worry about corrections to the legs and so on. There's many things that you can do, many diagrams that one has to calculate to do this carefully. But imagine you calculate everything, Okay, and in particular, if you're interested, this is done in great detail in section 16.5 of Peskin. And you calculate everything, and you can then figure out the analog of the scattering amplitude I wrote before, and it looks like this. Minus Ig, this is the tree level answer, plus Ig cubed divided by 4 pi squared. Let me write this down. This is 11 over 3n minus 2/3 nq Okay, so what's happening here? This n is the n in SUN, in other words, the rank of the gauge group. This NQ is the number of quark fields that we have. Okay, and E here is the energy flowing into the vertex. Okay, there's some characteristic energy scale involved in this process, and I'm calling E the energy flowing into the vertex. Now, I'm being deliberately vague with this, because the truth is, this isn't exactly what you do. It turns out there are many energies one could pick, and you don't really do exactly this if you want to demonstrate the physical point I'm making. The right thing to do is actually to calculate something called the beta function of the coupling G. Okay, and beta function of G. And this is something that is again discussed in the course on the renormalization group, which I encourage everyone to take. And over there, you really understand the kinematics carefully, and that gives precise meaning to what I'm saying here. But this is roughly correct, okay? This is roughly the right idea. Okay, now the crucial thing to note here is actually this sign, okay? The sign is the opposite from what we had earlier, okay? So what does that mean? That means that as you increase the energy here, the interaction becomes stronger and, the interaction becomes weaker and weaker and weaker, because now increasing the energy is acting in the opposite direction to the tree level result, and not the same direction. Okay. And this is true provided this sign is positive, which is again going to be true as long as NQ is kind of small. All right. So what I've just told you is that it looks like at high energies, as E gets bigger and bigger, this interaction is weaker and weaker. Okay. So in fact, if you take this very seriously, what this says is in the extreme ultraviolet, the interaction basically goes to 0 and you get a free theory. So this property is called asymptotic freedom. Okay? And it means what it sounds like in the extreme UV, in the asymptotics of the theory is free. This is an extremely important discovery, and for this, in fact, Gross, Politzer, and Wilczek, they won the Nobel Prize in 2006. And to understand why this is so important, we should think not about what this means in the UV, but think about what this means in the IR. If the theory is getting stronger and stronger, if the interaction is getting weaker and weaker in the UV, that means the interaction is stronger and stronger in the IR. Okay. So what happens when the interaction becomes stronger and stronger in the infrared? Because of course we actually care about things at long distance scales in the extreme infrared. So there are a couple of things that could happen. So one thing that could happen is that the theory could get Higgsed. And you studied this already in the standard model course, so I won't talk about it anymore. This, of course, happens in the standard model. The SU2 cross U1 gauge group in the standard model is indeed Higgsed. Okay, so this does happen in real life. And I won't talk about it anymore here, but you can still understand this often within perturbation theory. You just expand your perturbation theory about the new vacuum, and everything pretty much works out. Okay, so this is fine within perturbation theory. But let's assume this does not happen. So assume the theory does not get Higgsed. And in that case, the interaction continues to get stronger and stronger and stronger in the infrared. And now you have to believe me about what I'm going to say next. Again, if you take the RG course, you can prove this. It turns out if this doesn't happen, then the interaction, the gauge theory interaction, becomes infinitely strong at a certain energy scale. And that energy scale at which the coupling formally diverges is called in real life in QCD lambda QCD, and there's a formula for it. Okay. So here B naught is exactly this thing that appeared in our previous calculation. It's this factor here. All right. G square is the coupling, but as you know, couplings must be defined at some renormalization point, and E naught is that renormalization point. So at this energy scale, which is a physical energy scale, the coupling becomes infinitely strong, and this is called the strong coupling scale of QCD, or of non-abelian gauge theory more generally. Okay. At this point, technically the coupling diverges. Okay. So basically, once you get here, once you're this far in the infrared, you've lost all hope of doing perturbation theory. Okay. So techniques that we've used so far in this course simply do not work anymore. You have to really understand what's going on. And you see, this is why our classical intuition doesn't work. Remember I pointed out that the Lagrangian of QCD did not seem to match reality. This is really why it doesn't work. It's because the coupling has become very, very strong. Okay. In particular, at this scale, you expect bound states to form. Okay, so now we picture what's happening in QCD. In the UV, we have sort of quarks that do their thing. So here's a quark, here's another quark. They do their thing. Every once in a while, they exchange a gluon with some probability G, and that's all okay. So they're mostly free quarks and gluons, and you can study them with perturbation theory. The picture is very different in the infrared. In the infrared, the theory has become very, very strongly interacting, and eventually we don't understand perturbation theory anymore. Instead, the quarks bind themselves up into little bound states. Okay? Because the interactions are so strong that they don't let quarks come apart, they just get tied together in a tiny little bound state. And these bound states that you get are all gauge singlets. They're not charged under the gauge field. And again, if they weren't a gauge singlet, they would be coupled to the gauge field, which is infinitely strongly interacting. So every bound state has to be a gauge singlet, invariant under the gauge symmetry. Okay. These gauge singlets are the physical degrees of freedom. And this phenomenon, where the gauge charged degrees of freedom get bound up into bound states, is called confinement. Okay? It's the process by which gauge variant bound states are bound together. Gauge charged fundamental degrees of freedom are bound up into bound states. And all these bound states are massive, and in particular, there are no massless degrees of freedom generically here. Okay. So now, if you want to understand the spectrum in the infrared, you should ask yourself, how do we make gauge invariant states out of quarks? Well, there's basically two ways to do this. If you have a quark, you can imagine writing something like Q bar Q. Okay? This is gauge invariant because the SU3 rotation on Q bar cancels out that from Q bar Q. These are called mesons. Okay, and these particles exist in real life. So, for example, the pion is an example of a meson. Okay. Another way to do this, and this is using the epsilon symbol. You can also make a product of quark fields like this. This is also invariant under the gauge symmetry, and that's because this thing transforms like a factor of the determinant of the group element that's transforming everything. But the determinant of an SUN matrix is, of an SU3 matrix rather, is 1. So you can show this is also invariant. And these things are called baryons. Okay? And for example, the proton and the neutron are two baryons that we know and love. And I seem to have misspelled proton amazingly. Okay? And I want to emphasize that when I write Q bar Q, that doesn't mean that the meson is exactly a product of the quark field and the anti-quark field. This is a schematic picture to tell you about the quantum numbers that the meson carries. In reality, the quark and the anti-quark are really surrounded by a cloud of gluon fields. Okay, it's like Q bar Q, A. And these gluon fields do the job of gluing these two things together. Okay, this is really just a schematic. It's not a direct equality of field operators. Okay. So, and finally, let's note that we expect the mass of all these bound states to be around the mass of lambda QCD, because that's the natural scale for bound state formation. And lambda QCD is indeed around 200 MeV. And if you look, the proton and the neutron have masses around 938 MeV, which is not that far from there. The pions have masses around 135 MeV. This might seem weirdly low compared to the proton-neutron. There's a good reason for that. That has to do with chiral symmetry breaking, which I'm not going to talk about here. But there's a reason to explain that hierarchy. Okay, so basically this is how the physics that we know and love comes out of the QCD Lagrangian. It comes through confinement, which is when the interaction becomes extremely strong. Okay, so that's fine. But now I'm going to go even more qualitative. I'm going to try to give you a picture for what the gauge fields are doing in the confined phase. Okay, and this is going to be even more qualitative because previously at least there were some formulas. Here it's really quite difficult to write down formulas for this because the theory is strongly coupled, but we do have a very good physical picture for what the gauge fields are doing, which I'm going to tell you about now. So let's get oriented by first going back to U1 abelian gauge theory, which of course is Maxwell E&M. Okay. So now imagine having an electron and a positron separated by some distance r. All right. Now, as you know, the positron makes electric field lines which come out from the positron and go into the electron. Okay, so they look something like this. These are what the E field lines do. And because E&M is weakly coupled, we can actually calculate the energy of this configuration. And if you have an electron and positron separated by a distance r, then the energy of that configuration goes like E squared over r. Okay? And this is a calculation that you can do using elementary E&M. In particular, note that if you take these two things, the electron and positron, and move them further and further apart, the energy gets less and less, and so you can separate them. Okay, that's a perfectly reasonable thing to do. And this happens because the field lines sort of spread out. Okay, that's how the calculation goes. Now, this is not what happens in non-abelian gauge theory. If we try to do the same thing in non-abelian gauge theory, the analog would be to take a quark and an antiquark and try to separate them by some distance r. Now, because of confinement, because of the strong coupling dynamics of the quantum theory, what actually happens is that the color electric field lines, the non-abelian version of these electric field lines, they don't actually spread out. Instead, they form a tight little bundle, or a flux tube. Okay? And because they form a tight little bundle, it's really a flux tube, you can think of it as a physical object, this flux tube has a tension, and what that means is the energy in this configuration no longer decays with R, instead it grows linearly as you try to separate the quark and antiquark by a distance R. Okay? And that's just because you're pulling on this tube and making it longer and longer, and the tube has a finite tension. Here, I've called the tension of the quark tube of that flux tube alpha prime for some reason. Okay. But note what this means. This means that you cannot separate two quarks. To bring them infinitely far apart would cost infinite energy, and that's why quarks don't exist as asymptotic states. Okay, so you can no longer separate two quarks because they are held together by this confining flux tube. Okay, and of course that's the whole point of confinement. So in this picture, you can sort of see how to think about a meson. So you can imagine that a meson is kind of like a quark and an anti-quark pair, and there might be some vibrational modes. They're held together by a little string, and there might be some vibrational modes coming from how they wiggle back and forth, and that's how you can think of a meson. It's a quark and anti-quark tied together. Okay. Now this is pretty much as far as we can go. Okay. But let's imagine that, or as far as we will go, you can really go much farther. But let's imagine you're now trying to solve this problem. Okay, what will you try to do? Say you have this understanding. Well, one thing you might try to understand is try to understand the dynamics of the flux tube, right? You know there's a flux tube there. So you could try to understand this dynamics. And indeed, this is a program of research that was carried out with great, with lots of energy. So in particular, what you can do is try to take this flux tube as a starting point. Okay, and then try to quantize a theory of these flux tubes. Now, of course, these flux tubes are kind of like strings. So what we're really saying is try to imagine taking a theory of strings and try to quantize them. Understand the quantum dynamics of a theory of strings. So people tried this, and it's kind of really annoying because if you try to do this, what happens is no matter what you do, you always find a spin 2 massless particle in your spectrum. And if you're trying to solve QCD, this is a big problem because no matter what, there just isn't a spin 2 massless particle in the QCD spectrum. Now, eventually what people realized is that actually this is solving a different problem. This spin 2 massless particle is in fact the graviton. And in fact, the theory that you get if you quantize strings is not directly QCD, but is instead a theory of quantum gravity, so something much more powerful than it had originally been anticipated. So a lot has happened since then. We now know how to think about non-abelian gauge theories in the picture of string theory. But I think this is where I'm going to stop, and this is the end of the course. So we're finally done, and so this is officially the end. And before finishing, I just want to thank everyone for all of your attention during this course. I know that this was quite a weird format for me to be teaching in. But thank you all for your attention. It's been great teaching you, and I know from all the questions that you've asked in the various surgeries and through emails and things like that, people have actually really paid attention to what's been going on. So thank you for that, and I will continue to see you in other guises, I'm sure, as the term goes on. Thank you.